we finished talking about step index logical relations being used to prove type safety in the presence of recursive types. And then I started to talk about the use of logical relations for proving contextual equivalence of programs, to prove that two programs are contextually or observationally equivalent. So in that context, today what we're going to do is we're going to start out by taking essentially the unary logical relation that we had defined yesterday for type safety. In a sense, what we're going to be doing today is editing that and turning it into a binary logical relation. And I want you to see how similar the two are. You know, a lot of the ideas that we've already built in that unary setting for type safety extend over to equivalence. So yesterday, I defined what equivalence, you know, I gave a formal statement of contextual equivalence. So let's just put that up again. Actually, let me split it up into 2 bits, which I did not do yesterday, but let's do it now. Contextual approximation and equivalence. If this pen runs out, please someone scream. Okay. So instead of defining contextual equivalence directly like I did yesterday, I'm going to, oh, and by the way, at the very end of yesterday's lecture, I added, you know, universal types and existential types to our language, right? That's up on the board. In fact, assume that the stuff that we have now is Booleans, functions, recursive types, and polymorphism and existential types, all right? I've just left out most of the syntax for the earlier stuff. Yes?
Find the contextual difference using a termination, but I don't really see how we can have one termination in this language yet. How can we construct looping?
The language up there?
Yes.
The language up there does have recursive types in it.
Okay, but how can you use recursive types without a fix to get something that loops?
You don't need a fix. You can define, so now essentially, remember omega, diverge. Type setting, it's lambda xx applied to lambda xx. Right? You can type check this in the presence of recursive types. So you can loop. How? Can we do that offline? Okay. Is this obvious to most people? It's a what? Okay, let's try to, okay, let's take 2 minutes and try to do this. Mu alpha, alpha, or alpha? Yes, I think that'll do the trick. Yeah? Okay, let's see. Okay, so let's, all right. Okay, so, okay, let's do it just from absolutely first principle. We want to write down a type for this. We have recursive types in the language. All right. So what type might we want to write down for x is sort of the question to start out with, right? X has to be some sort of function type, because it's being used there. Okay, so what could we use? Xavier just suggested mu alpha, alpha, or alpha. Why am I giving it a recursive type? Well, it needs to be, a recursive type allows us to shift views between the function type that's inside it and the outside recursive type, right? So we can shift views between this and alpha, alpha arrow alpha, which is this tau, right? With mu alpha, alpha, or alpha for alpha, right? Okay. In other words, so we can use unfold to shift views to this and fold to go back, right? Okay. So this guy has a recursive type, this x, and so does this. Well, that's a problem. That won't really type check. So instead, what we'll do is we will unfold x in this position before we apply it to that x. Now, this makes sense, right? Once we unfold, we have this type. This x has the right argument type. So now we're good. So you see that this type checks? Okay. Same thing, same story on this side. And then I think we need to add another either fold or an unfold in one spot. Should I go on? Should I keep going on? I see nods. Okay, fine. We'll keep going on. Okay, so we do the same thing on this side. We have lambda x, mu alpha, alpha, or alpha. Unfold x, x. All right. Now, what's the type of this whole thing? It's this type right here, right? And therefore, the type of this whole thing is this same type. So this is a function type, and it's taking an argument. That's good, but the argument that it wants should have its argument type. And how can we get that? Simply by putting a fold out here before we pass it in. There we go. We can diverge in this language. Okay? All right.
We know that we can remove this non-termination, but these are only recursive arguments in negative position.
Yes, but we are allowing full recursive types.
If we did that, would we still have interest in the index? I would say yes, because we still have this.
We still have
definition.
yes, yes. Even if you took out recursive types entirely and just threw in recursive functions, I would still.
That's the way
But that's
right.
right.
I mean, the state index is mostly for non-termination at type level or term level? Because if we had a people in the term level, would be.
It's not that you. So that's what I meant. If you just took out recursive types from this language entirely, and instead just had recursive functions, so recursion at the term level only and not at the type level, then obviously all of the motivation that I showed you for the interpretation of real alpha tau, right? I said, oh, the types are getting bigger and the step indices are going to help us deal with that. That's basically what your question is about. That do we still need step indices and index recursive types, but we just have recursive functions? And the answer is yes, they're really helpful. Because if you don't do that, then you can make things work out without step indices. But to do that, you now have recursive functions, so you need to show certain admissibility properties about the logical relation that you've set up. So a good reference for this is in Benjamin's second book, The Advanced Topics on Types in Programming Languages. Andrew Pitts has a chapter, I think it's called Typed Operational Reasoning. And what Andy Pitts does there is he basically sets up a logical relation for system F existential types and recursive functions. They did not know how to do, and it's an operational logical relation in this style. At the very end of that chapter, he poses an open problem. He says, okay, in this chapter I've used this, so he uses things like Galois connections and so on, and proves a recursive unwinding lemma for recursive functions. That's how he basically shows the admissibility properties that you need for the relation that you set up. But then at the end of the chapter, he poses this open problem. He says, we do not know how to extend this technique to recursive types. Okay, when was this published, Benjamin? ATAPL? 2003? Yeah, okay. So basically right around then, step index logical relations came about, and now we know how to do this for recursive types rather easily. Okay? All right, so if you want to see that formulation, you can look at this chapter. You can do it without step index. Okay, so yes, we have non-termination in our language. So let's go back to contextual approximation and equivalence. So here's what I want to do. Oh, by the way, we have polymorphism in our language now. So let's, yesterday I was just doing E1, I was doing contextual equivalence. Today I want to split it up into two phases and first define a notion of contextual approximation. So if E1 has type tau under gamma and E2 has type tau under gamma, then we say that E1 contextually approximates E2, and in a minute we'll define E1 is contextually equivalent to E2 as well. But today we also have polymorphism, so I'm going to add a delta there. Just really natural extension, read in exactly the same way. All right, so we're going to define this as if you give me some context C such that C is has this type of hole. So now, yesterday my hole only had a gamma and a tau. Today the type of my hole is going to need a delta as well because we've added polymorphism, right? So I'm just taking the type of the hole just like I did yesterday from here and here. So that's the type of the hole of my context, and for the full context, after I've plugged it in with the appropriate expression, I want a closed expression. So I want both delta and gamma to be empty, and the result type can be any arbitrary type prime. Let's put that out here. This is for all type prime. Okay? So if you give me a well-typed context with a hole of the right shape, of the right type. And then you plug in E1 into the hole. If that terminates, then C with E2 terminates. So approximation says if the expression on this side terminates, then the expression plugged into the context on that side terminates. Okay? Yesterday, equivalence was in both directions. So equivalence is just obviously then contextual approximation in both directions, right? E1 is contextually equivalent to E2 if E1 contextually approximates E2 and E2, sorry, at the type tau, and E2 contextually approximates E1 at the type tau. Don't I want what? Over here? Read it like this. So if this and this, then this. Yeah? You could write it as if this, then this implies this. That's essentially what it amounts to. Yep. Okay? So the reason I split it up into approximation and then doing, defining equivalence using the definition of approximation is because if you sort of do equivalence directly, you're doing the proofs in both directions anyway. This just sort of allows you to do, in a sense, half as much work and then just reuse the work you've done. Okay, so we'll be proving contextual approximation through the rest of the lecture. Okay, so I want to start, as I said, I want to start editing the unary logical relation that we had up there yesterday. So yesterday we basically had something like this. We wanted to know, the notion that we wanted to define, interpretation of type tau for k steps, right? A value v belongs to or behaves like it has the type tau for up to k steps. This is what we were defining yesterday. Today, we want to define a logical relation that captures the notion of equivalence. What we want to set up is a binary logical relation, which should be read as the value v1 contextually approximates, or logically approximates. You can call it whatever you like. Or you can call it is related to or is equivalent to. That's most precisely the notion I'm going for is that v1 contextually approximates v2. That's what we're going to try to capture, but without using the definition of contextual approximation in here. Okay, so v1 and v2 here both should have the type tau, and I'll formalize that in a bit. Actually, why don't I do that right now? I'll do that in a second. And what this says is that for up to k1 steps, v1 looks like it's equivalent to v2. Okay, let's just stick with that intuition for now, and then we'll hone it a little bit as we go. I'm going to make sure today that these are well typed. So let me just put up a couple of one predicate. I'm going to define the set atom as sets of expressions E1 and E2. In fact, I shouldn't be doing this yet. I'll come back to this in a second. What I was going to add over here is that E1 has to have the type tau, let's say well-typed atoms, and E2 has to have the type tau. By the way, I'm not going to be disciplined enough to put 2 dots out there. If there's nothing before the turnstile, it's an empty context. Okay, so closed expression. All right. So, at the type Boolean, when are 2 values v1 and v2 equivalent? What do I want to put there? When they're the same. Exactly. So let's just say v is equal to v, right? They're both the same exact value, and we can say that v equals true or v equals false. Okay. How about functions? we're going to have two lambdas in here, right? Lambda x colon tau 1 E1 and lambda x colon tau 1 E2. So when do two functions look like they're equivalent? Oh, to the same term? Yes, exactly. So what we want is, we want to say, right, we've been saying this about logical relations. If you give me related inputs, I will give you related outputs. This is where that comes in, okay, at the function type. So what we want to say is that if you give me two related inputs, v1 and v2, that are related at the argument type, sorry, here we want for all j less than k, right, for all the reasons that we had for all j less than k yesterday, we're keeping that the same. Then sorry, question? Let's finish this. E1 with v1 for x is going to be an expression that's related to E2 with v2 for x. For the remaining j steps at the result type tau 2. Say that again? Oh yes, this is tau 1. Absolutely. Thanks.
Why is that local covariance happening to have a
It's not happening yet. I'm burying that into the definition of expression. So let's look at that next. Okay? Because it's approximation that I'm defining, right? Not equivalence. So far, everything looks like, oh, related things going in, they could be and related things coming out. We'll capture the notion of approximation here. When now we have expressions E1 and E2. And what we want to capture here with this relation is the notion of approximation, not equivalent. So we want to say that if E1 terminates, then E2 will terminate. And you will get related values. Yes.
If you have that, if you would expect V1 is to be swapped on the negative side of the thing.
No. You always want to keep, there's no swapping in that sense, no. And we can talk about it more later if it's still confusing. Yes. You always keep your program 1 on the first side and your program 2 on the second side. All right? Okay. Okay, so yes, just like I did before, I buried something into the definition of the E relation, right? I just said, okay, you give me some related inputs, I plug them into the bodies of the lambdas, and I get related expressions. And so far, I'm just using the word related. Okay, so this is where we want to capture what we mean by related. What we want is the notion of contextual approximation. So we want to say that if E1 terminates, then E2 will terminate, because that's the notion we're looking for, right? And also, this time I'm assuming that the language that we have has already been proved type safe. I'm not using my logical relation to prove type safety. I'm assuming that we're building the logical relation out of well-typed terms. That's why I put atom up there, to very explicitly say that we're building it out of well-typed terms. So we can just sort of go ahead and say, for all V1 such that E1, I forgot, j less than k, for all j is strictly less than k, for all V1, if E1 in j steps reduces to a value V1, so I'm not going to say reduces to an expression, and if that expression is irreducible, etc., right? There's no need for that. Okay. Then there exists a V2 such that E2 reduces to a value V2. And we also have to say that the resulting values that we got, right? So far we've said if this side terminates, then this side must also terminate. We also now need to say that V1 will be related to V2 at the type tau for the remaining number of steps, which is k minus j. Yes?
Should you use j there instead of
Very good. I was waiting for that. Why have I put a star over here when I put a j over here, right? So this j is less than k, so it, what I'm following is for For the left-hand side at least, right, for the expression E1, I'm following the intuition that I gave you yesterday, which is that E1 looks like it has, or looks like it has type tau for up to k steps. Today I sort of use the sentence E1 and E2 look like they're related for up to k steps. This time it's slightly misleading. Here we really do want this k to only be bounding the number of steps on one side, all right, not on the other. And let's talk about the alternatives. You could try to set up this definition so that the k limits the number of steps that you can take on this side as well. So that, you have either, what if I put exactly j over here? That would mean E1 reduces to a value in exactly j steps, and E2 reduces to a value in exactly j steps. Why is that bad?
You are going to prove a theorem about the number of steps you actually need to use.
Right.
We've a notion of contextual.
Yes, our notion of contextual equivalence doesn't say that these two sides have to terminate in exactly the same number of steps. If I put a j over here, then my logical relation is demanding that you have to terminate in the same number of steps, and that doesn't make any sense, and it's not an interesting notion of equivalence. I mean, suppose I just wanted to show that 1 plus 1 is equal to 2. Here I'm taking 0 steps, here I'm, right? It doesn't make sense. We don't want the same number of steps on both sides. The only time you might want the same number of steps on both sides is if you were doing sort of security in the way that Andrew is doing, and maybe he can say a bit about that later. It's about timing. It's about sensitivity to timing, right? We're not building a logical relation that's timing sensitive. We're trying to capture this notion of contextual equivalence. Okay? All right. Now, a few years ago, I actually tried very hard. This was a very, very confusing notion. And the fact that there's no step index here actually leads to weird sorts of problems when you start to prove that the logical relation is transitive. So when you start to prove that if E1 is logically related to E2 and E2 is logically related to E3, you want to show that E1 is logically related to E3. And I couldn't do it. So I spent a few months actually trying to set up something where I was convinced that, this step needs to bound the other side as well. But no matter how you do it, you could try to use k to somehow bound this, using some other j prime that's less than k. You could use a k1 and a k2, one for one side and one for the other. But in the end, when you're done defining what looks like a sensible logical relation, every single time I ended up with something which was demanding that both sides take exactly the same number of steps. So we have now sort of understood this problem, we who do step index logical relations, and this is the right formulation. And what this comes down to is this intuition that I've been using. Worked very well for type safety, right? This value v looks like it has type tau for up to k steps. When it comes to equivalence, the intuition is slightly misleading. Because after all, what this k is a metric that's allowing you to do induction. Okay? Ultimately, that's what it is. And this is sort of one way in which that's showing up. Any questions? Yes?
Why can't this another j prime which is also less than k and j prime?
Because if you insist that that j prime is also less than what happens when k is 1? J and j prime will both be 0. So you're demanding that they both terminate in the same number of steps. Sort of. I mean, that's roughly what it comes down to. When that's what it collapses down to. So you'll just have to take my word for this. And we can talk more about it later if it's not clear. Yes?
This definition does cause problems when you try to prove transition?
It does, but we know how to solve it. It does if you're setting up your logical relation with untyped. If you're setting up your logical relation the way we are setting it up with typed terms, it does not cause any problems. And if you want a reference for this, so all of this came up back in 2006, and for this transitivity issue, and in fact for this entire lecture that I'm doing today. A very good detailed reference is this technical report that I wrote back then. So this is with my ESOP 06 paper. It's called Step Index Logical Relations for Recursive and Quantified Types or something. But it's the technical report that comes with that. It's the our extended version. I don't know how it's listed on my homepage. That's like this really detailed, long thing. It's like 168 pages or something, and it has all of the proofs of all of the cases, and the whole thing worked out, step index logical relations for proving equivalence and, with recursive types only, and then again after we add polymorphism and existential types, and talks about all of these subtleties and transitivity and what happens when you have existential types, which is another issue. Yes.
Years than this definition for equivalence.
For what?
For equivalence instead of approximation.
So the definition of the logical relation, how do we extend it? Okay. So we don't really need to extend it because right now our E relation is capturing approximation. We are going to define E1 approximates E2 at the type tau in a moment. Once we've done that, we are going to say that E1 is logically equivalent to E2 at the type tau if you have approximation in both directions. Start putting deltas here. So if E1 logically approximates E2 and E2 logically approximates E1. At the type tau.
Equivalence to approximation isn't just a question of saving symmetric cases in the proof. It actually wouldn't work.
It actually wouldn't work. I mean, because of this inherent with the number of steps. The K is bounding only this side. There are some nifty little things you can do in order to set up a more symmetric version. And I've been doing that recently. A reference. Not one that's easy to understand. But in a sense, if you wanted to add symmetry over here, you have to do it without changing this, right? This has to remain asymmetric. The step index should only bound the number of steps you can take on one side. So if you wanted to make this relation symmetric, I would add another conjunct that simply says all of this stuff, and for all j less than k, for all v2 such that e2 reduces in j steps to v2, then there exists a v1 such that e1 reduces to v1, etc. Okay? Yes?
I'm trying to fix your last comment. Answer questions in my mind. So, would it be correct to say that the intuition that we got from the application of this to typing, that the values in BK look like things of the appropriate type up to a certain number of steps, was fine for that example, but misleading for other examples because it over-constrains the set of definitions that we're willing to look at?
I think that's fair. If you want to apply that sort of intuition here, you have to keep in mind that the K is bound on the sort of observation power of the context on one side.
And is the intuition why we only need it to be bounded once, that we're only going to do induction on, we're going to sort of be given two typing derivations, but we're only going to do induction on one of them? Or something like that?
No, not quite. Maybe we'll come back to this later. Think about a better way of saying it. Okay. All right. So let's, before we go any further, let's finish up, let's add recursive types, an interpretation for recursive types. And then, more importantly, let's look at how we would handle polymorphism and existential types. Okay? So recursive types. So this time we want to say that we have a fold V1 and a fold V2. So fold V1 is related to fold V2 for k steps at mu alpha tau if what? What did we have yesterday? We had for all j less than k, the value sitting inside the fold belonged to the unfolded type. right? So we're going to do the same thing, except this time we're going to say v1 and v2 are related at that time. So v1, v2 are related for j steps, where j is less than k, at the type tau with mu alpha tau for alpha. Okay? So far it's really a completely straightforward extension. All of these are really just turning unary things into binary things. We haven't done anything else. The only place that was interesting is here, where we wanted to capture the notion of contextual approximation, and this issue with step indices came up, right? Okay, now, more space. Okay, we'll do it here. Let's handle polymorphism. So for k steps, we want to say, when do two values of type for all alpha tau look related? What are the values of type for all alpha tau? Big lambda alpha, right? So lambda alpha E1 is related to lambda alpha E2 if what? Here's the definition for functions. And let's think about what we would do here. What do we do with functions? We ask the question, well, if I give you a function and I ask you, does it behave like it has this type? What do you do with it? You apply it, etc. Right? That's how we came up with that definition. So similar story for type abstraction. If I give you a type abstraction, big lambda alpha E1, what do you do with it? Okay. So you apply. Okay. So answer one, you apply it to a type. So we're going to have to say, give me some type. But now the next question is, do we want to say, give me the same type for both sides? Or do we want different types, tau 1 and tau 2, for the two sides? So I just got two no's. No, you do not want the same type for both sides. What?
Relate them.
Relate them, exactly. Okay, so the reason we don't want the same type for two sides is, I don't know, I mean, you could have a function, take some alpha, give it 5, right? Here's a function. If I apply this to bool and true, what will I get back? 5. But I could also apply it to int and 0, and I would still get back 5, just to take a really, really trivial example. So we do want to, we're trying to talk about equivalence of two different programs, and we definitely want to be able to relate, to apply them to two different types. Up there, I have the example of the existential type. I mean, it's existentials, but it's the same sort of intuition. We have an exists alpha, and we're packaging up an alpha with a function from alpha to bool, right? And here we have two different witness types, a tau 1 and a tau 2. So we need two different types here. We want to say, give me a tau 1 and give me a tau 2. And then what? Then we want to say that E1 with tau 1 substituted for alpha should be related to E2 with tau 2 substituted for alpha. These are expressions, so we're going to use the expression relation. We also want to say for all j less than k over here, because it's analogous to what happens with functions. You have, this time a type abstraction. It's like a function. It's a suspended computation. You could apply it now or at some point in the future. So the same intuition. So you can think of this as at some point in the future, someone gives us these two types, and we want to do the application, the instantiation. Okay. So now these should be related at what type? We have to somehow prove that both types are equal, or we have to relate them at the inset, right? Okay, well, let's just naively. What should I start putting here? Tau? Okay, so these guys have type for all alpha tau, right? So the underlying expression E, let's look at the rule up there for type abstraction. For all alpha E has type for all alpha tau. Sorry, lambda alpha E has type for all alpha tau if E has type tau with alpha in the context, right? Okay. So we want to relate them at tau, but the problem is that tau has alpha free in it. So should we try to close it off with something? We could close it off with tau 1, but then we would get that this expression has type, I mean, this expression does have type tau with tau 1 for alpha, right? This expression has type tau with tau 2 for alpha. How are we going to put the same type over here? Tau 1 and tau 2 can be different types. Sorry, say that again? Okay, so, all right, so basically what we're going to do is, right now we've been defining interpretations of closed types. We now have type variables. We had type variables when we had recursive functions as well, but we could get away without defining the meaning of B alpha before. We didn't need it because in the definition of recursive types, we know exactly what to substitute here, and it's the same thing for both sides, so to speak. So we could get away with just giving interpretations of closed types. Now we can't do that anymore because we want to be able to relate, like as you can clearly see in this case, we want to be able to relate things of different types. Okay, abstraction comes into the picture. All right, so basically what we need to do is start defining interpretations for open types. And I'm going to do this by parametrizing this entire logical relation with an environment, which I'll call rho. Rho is going to be a mapping from, rho is going to have the form alpha maps to tau 1, tau 2, etc. You know, a bunch of these. So basically, rho is going to allow us to keep track of the types that we picked when inside the for all case, the types that we picked for one side and for the other. It's a way of remembering that. Okay, with me so far? All right. So let's see if that does the trick. The answer is it doesn't. But let's see where. All right, so I could just, here, none of these earlier definitions used rho, so let's just plop rho everywhere, and it just gets carried around without being used by any of these. If I missed a spot, let me know. Oh, here, of course, we need to be careful now. Also, when I write rho is something of this form, I'm going to use the following shorthand. I'm going to write rho 1. So if rho looks like this, I'm going to write rho 1 to mean the substitution that maps alpha to tau 1, and similarly for all the alphas, for all the other alphas, pick the type on the left side. And I'm going to write rho 2 to mean the substitution that maps alpha to tau 2, where that's the second type. Okay? So that's going to be my shorthand. All right. So here then, to be careful, we need to make sure these are no longer closed expressions, right? So this term is going to have the type rho 1 of tau 1 to rho 2 to rho 1 of tau 2. You see that? Or more generally, where's Adam? We are allowing these two terms to have two different types, tau 1 and tau 2. Okay? And we are building every one of our view relations so that whenever we have V relations or E relations, whenever we have E1, E2 belong to E tau with a rho, then this guy has type rho 1 tau and this guy has type rho 2 tau. Okay? That's just the slight stuff you have to be careful about here. Okay. So here, rho 1, here, rho 2. Okay. Yes?
With the argument, you still get the same one for both arguments, but wouldn't it make sense to also generalize the second one to the
It is being generalized. the argument type of this function is row 1 of tau 1. And the argument type of this function is row 2 of tau 1. Because we're talking about the argument. Yeah, perhaps if you write the tau or tau prime, then the 1 and the 2 don't get confused.
So it's just that we're not doing it for, like, you can think of the two functions being different and then you're relating them to them.
So are you talking about, for instance, like let's take a look at this example. Once we've applied it to the rule, in the first case, we end up with bool size applied to true. And in the second case, we end up with int size applied to 0. That's your concern, right?
Yeah, but I guess if we just generalize the alpha.
Yes, we're just generalizing the alpha, right? The row is keeping track of what the alpha goes off with. So this is allowing us to generalize that. I put row 1 of tau 1 here and row 2 of tau 2 here. The argument, the actual concrete argument types of these functions can be different. If row maps any free type variable in tau 1 to different types, then the arguments of these two functions will be different. Okay? All right. Now, let's come back to this. Okay, so said let's add rows, and now we have a row coming in, and what we're going to do is this tau, so all of the free type variables in this type were mapped to something by row, right? Now this type tau has one extra type variable than we did before, so we need to map that to the things that we've just picked for the two sides, which is tau 1 and tau 2. Fair enough? Yes. Yeah.
Row are consistent, or by your assumption of the language is already type safe?
No, you have to, you need to know something about that, and that's exactly what I'm getting to next. But let's look at it in the context of fine. Now we're doing interpretations of open types, right? So we need to be able to handle the case where tau has free type variables. So how do we interpret alpha? What are the values that belong to alpha? Or what are pairs of values v1 and v2 such that v1 logically approximates v2 at the type alpha? Yes?
Plug in any type and it would work the same?
Well, that's the issue, right? So what do we know at this point? The only thing we know is that rho gives us a mapping from this alpha to some tau 1 or some tau 2. We know that, right? Okay.
Oh, so we can look up.
Which means that we know that this guy has to have type tau 1, this has to have type tau 2. You with me? Okay, but we know nothing else about what relationship we want between them. When are they related? And this is the thing. That's why it's when we pick two arbitrary types, right? Like in our example, when we picked, let's go back to writing it that way. Lambda alpha, lambda x alpha 5 applied to bool and true, and similarly applied to int and 0. Here, I picked a tau 1, I picked a tau 2, all right? And I gave them to this type abstraction as inputs, but after that, I have to give it an input of type alpha, right? So I'm choosing to give it true and 0. Basically, my point is here, at this point in time, I'm saying, here, from now on, consider these two completely different types to be related. So at that point, I also have the obligation to give you a set of values of the types tau 1 and tau 2 and say when they are related. So I need to have a relation R that tells me when values, so let's write this a bit more precisely. We want a relation R from something that I'm going to call rel of tau 1 comma tau 2. Is that too squished? Should I rewrite? R, so for all tau 1, tau, and all tau 2, and for all R that belongs to rel of tau 1, tau 2, which I'll define in a second, we need to show that E1 with tau 1 for alpha is related to E2 with tau 2 for alpha. For J step. Okay, what is rel? Have people heard of Girard's candidates method? Okay, for those of you who have or haven't, let me just say a few words. So Girard's candidates method was basically a method for proving strong normalization for system F. All right, and the main observation, or the relation to what we're doing now is when you get to this part of your definition in system F, when you try to define the interpretation of polymorphic types, you get to pick an arbitrary relation here. You can't just pick an arbitrary relation. It needs to have certain constraints on it. Otherwise, your logical relation as a whole won't be consistent in various ways. Okay? So just keep that in mind for now. So let's figure out what those conditions are that we need to impose. So we're saying you can go pick an arbitrary relation. Let's figure out what that is. Now, this relation should map I'm going to erase by the way, just like I had row 1 for alpha maps to tau 1 before, and row 2 as shorthand for alpha maps to tau 2s, I'll write row R for the third component that I'm storing in there now. Okay? Again, just shorthand. Let's leave that to the side. Okay, so what is rel of tau 1 comma tau 2? I think I need one moment's digression before I do this. Since yesterday, I've been defining. Yesterday I defined these as sets of values. Today I'm defining them as relations on values, right? I just want to get one notational thing out of the way. So yesterday this was basically a member of power set of closed values, right? Yeah? Because it's a set, it was a set of closed values, so it's a member of the power set of closed values. Today we're doing relations, so we want that, right? Okay. Furthermore, the values that I put in here, I want them to be well typed. So instead of writing that, I'm going to say that these actually come from take atom, restrict it to the values, and make it a power set of that. You with me so far? So I went binary. Atom is just defining when two expressions are related. So it's also telling us when values are related. All right, so this is just a set, or this time a relation on closed values, which I'm getting out of here. But the only extra restriction that Atom is placing on it is that I'm saying that my values or my expressions have to be well typed. With me so far? Yes?
What does val mean?
Oh, val. Take the set atom, tau 1, tau 2, and when I put the superscript val on it, that means take only the subset which has values in both equations.
So no general expressions, only values?
No general expressions, only values. The value restriction on that. Okay. Now, I'm going to, I just want to make this obvious. When I drop the step index over here, I want to, well, we should be thinking of that as a function from nat to power set of, again, yesterday it was closed values. Are we good with that? Just a function, right? Because I dropped this step index over there. Okay, I just want that notation to be like clear. All right. But again, here today we are going to say that we want relations, and relations built out of well-typed values. All right. So let's put that on the side. So the relations that we want should be relations that can accommodate these things that we've been defining. All right. So what we want is rel to be something drawn from functions from the math to the power set of atoms, restricted to values. And in particular, I want I want these things to be relations on values of type tau 1 on one side and values of type tau 2 on the other side. So I get to put that here. Okay? I'm just doing basic set theory functions. All right. So that's for starters the space that these relations are drawn from. Yes.
We always inhabited by some type.
Are the types always inhabited?
Yeah.
Okay. Well, the types that we have so far in our language are certainly inhabited. Right? So tau 1, tau 2 are syntactic types, and if you look at what types we have in our language, they are certainly inhabited.
The user can define their own type.
Yeah, you could define for all alpha, right? That's a void type, right? It's not inhabited by anything. But they're not. I mean, so for all alpha is the void void, right? It's not inhabited. But not about. Yes, absolutely. But this is not an issue. So just this is an arbitrary relation. It could be empty. Fine. Okay. Now, so we want this relation to be a value relation. It relates values of type tau 1 to values of type tau 2. What else might we want? What other properties might we want this relation to respect? I said that we're going to be sort of, sometimes want to instantiate these R's with these guys. What property did these guys have yesterday? They were downward closed, right? So we want that, or this monotonicity property. So we want that same property here. We want to say that for all k and for all j, if j is less than or equal to k, then R of k should be a subset of R of j. Right, just a shorter form of writing what I was writing. So if v1, v2 belong to R of k, then v1, v2 should belong to R of j. Okay? Or another way of saying it, if two values are related for k steps, then they're related for fewer steps. Okay, so with that out of the way, let's go back. Now what we've done in our interpretation of for all types is we have picked two arbitrary types for the two sides, and we are letting you pick, or letting anyone pick, a relation R that relates values of type tau 1 and tau 2. And from then on, we are going to keep track of that relation R. And you know how logical relations say, if you give me related inputs, I will give you related outputs? Let's take a look at what if we had the polymorphic identity function here, right? I am going to pick two different types, bool and int, to instantiate this function. Right? So I'm taking the same function, applying it to bool on one side and int on the other side. And then I'm passing in true over here and 0 over here. And what will I get? And what I want at that point, if I want to sort of establish that this function always takes related inputs and gives me back related outputs, the intuition is that you want to set your relation, your R, up in such a way so that it says R is true is related to 0. It could just be that singleton relation, for instance. All right? And then what we're doing is we're feeding related inputs into the function at the type alpha, and we will get back related outputs at the type alpha. Maybe that'll become a bit more clear later. Okay, so now, where?
The R equals set of 0.
Yes, I do need some R set. Thank you. Okay, so now I could write this as a set of all values v1 and v2 that belong to rho of alpha, rho, pick out the R, alpha at this step level k. More concisely, I could just write it as, let me write it as a more concise thing, which is just that. Right? So in other words, when you instantiate the alpha in the for all case, you get to pick a relation. When you get to asking the question, as you drill down into this type, at some point when you get to asking the question, hey, here's a type alpha. When are two values related at this type? All you do is you just go ask the relation that you've been carrying around in the row. If that relation says that, yes, these two values are related, then they're related. Yes? Well, so this relation comes up when you try to do examples, right? When you try to do, for instance, a proof of the free theorem that I put up. That's where this method gives you sort of the right points to specify a relation and then use the relation that you have specified to prove the theorem of interest. And we'll see that with the free theorem. General equivalence relation. No, it's not that. See, think of this as like let's take a look at what you would need. Actually, let's come back to that in just one moment. Let's define existential types, and then I want to look at that example, and I think that'll answer your question. Okay? Where do I put existential types? I'm going to erase recursive types and just do it here. Okay, ink cartridge. I'm probably going to have ink all over me today. Sorry, thank you. I think the cap got stuck. Black, hopefully? Yes?
So, what's different for me that we don't put any constraint over R, like it should be reflexive in some way. Because
so you don't. Okay, we're going to come back to this as well. So what you would want from R is only one condition. So if you, I'll give you a technical answer right now and explain it. Okay, technical answer right now is that the definition that we're building right now is good enough without any extra constraints on R. If all you want to do is have a logical relation that is sound for proving contextual equivalence. If you want a logical relation that's also complete with respect to contextual equivalence, so in other words, contextually equivalent, they should be in the logical relation, then you need to constrain the R a little bit more. And we'll come back to that. It needs to observe it needs to respect equivalences. So whenever you put two values, whenever you say two values are related in R, it better be the case that if those values are equivalent to other things, then those things should also be related. So, yes.
Where are we actually using the VK alpha?
VK alpha. Okay, you will use it. You will end up using it. So suppose that this tau, in the concrete case where this tau was actually alpha arrow alpha, look at what would happen, right? We would be saying that these two terms are related at E of tau alpha arrow alpha, and then we would go here, and this is now alpha arrow alpha, and this definition says something about these values being related at the function type at tau alpha or alpha. And now if we unwind the definition of function type, where this is alpha and this is alpha, right here, this will be alpha. And this will be alpha. So it's because the logical relation is defined by induction on type, eventually that's your base case, or one of your base cases, along with Boolean. Yeah? Okay. Existential. So when are two values related at existential type? What are values of existential type? Pack. Yes. Okay. So we want to say that a pack tau1 v1 is related to a pack tau2 v2 if something. And again, here we're allowing two different types on the two different sides, right? Just like I'm doing in that example up on the board, and we've already talked about this for universals. Okay, so how do you think we need to define this? Look at the typing rule for pack. The expression that's sitting in the package has type tau with tau prime for alpha, right? So this guy has type tau with tau1 for alpha. This guy has type tau with tau2 for alpha. We have the same sort of situation again that we had it with universal types, right? So we basically just want to say that v1 is related to v2. And these are just values, so we don't need to appeal to the expression relation. We want to say that they're related at the type tau with rho extended with a mapping from alpha to tau1 for the first side, tau2 for the second side, and now we need a relation R. So basically we want to do, here do we want to say for all R? No. We want to say there exists an R, exactly. There exists an R in rel tau1, tau2, where tau1 and tau2 are the witness types for the two packages. Okay. And we should do for all j less than k out here and j over here. Same intuition as before. All right? Okay. By the way, exception mixing or not, logical relations for just pure system F, and existential types without any recursion, non-termination in the language, you would just get rid of everything on the board that talks about steps, and essentially you would have the same set. Okay? All right. So let's extend this to open terms. So far we've been talking about closed values being related and closed terms being related. So what do we need to do for open terms? These terms are open, so they have free term variables, but they also have free type variables. Right? We didn't have this yesterday. So just like we were picking gamma, a substitution that maps our term variables to values, we now have this rho, a substitution which maps our type variables to the types for the two sides, right? The tau1s and the tau2s. And of course a relation as well. So we kind of need to close off these terms and then talk about them being related in the E relation. Very similar to what we did yesterday. All right? So, okay, let's define G of empty is just going to be, at K, is just going to be two empty substitutions, right? We're making everything binary, so now we have two substitutions here. I'll just move over here. G of gamma x colon tau with a rho. By the way, we have rows here now because the codomain of this gamma can have types with free variables, right? And those free variables will have to appear in here. So that's why we need to parameterize G, this relation with rho as well, because it contains bindings that close off these. Okay, so here, yesterday we had one substitution, now we're going to have two. So we have gamma 1 maps x to v1, and gamma 2 maps x to v2. Like that? Yeah, thank you. Okay, so these two substitutions are related when gamma 1, gamma 2 are related in G. Let me erase this. Are related in G of gamma for k steps, and the V1, V2 are related according to the value relation for k steps. So very much like yesterday, the row here, except binary. But now we need to say something about how we pick a row to close things off. Okay, so here, basically when we define approximation, we're going to do this sort of similarly to yesterday. First we're going to say, give me an arbitrary k that's greater or equal to 0. And then I want to say, give me an arbitrary row and give me a gamma. Gamma 1 and gamma 2. Gamma 1 and gamma 2 we know have to be related according to this, but we want to impose certain constraints on rho as well, where we're going to require that rho belong to d of delta, that rho be an appropriate substitution given our type environment delta. And we're going to do that this way. So if delta is empty, then rho is simply the empty substitution. If we have delta alpha, then we want a row that maps alpha to some tau 1, tau 2, and r relation, right? And this is an appropriate thing to pick for this. It satisfies this type environment if, well, first we want to say rho satisfies delta, and the relation that we have just picked, just like we did in the definition of universal type, better belong to rel of tau 1, tau 2. Okay? So basically, this is the point where we, actually this point and this point in the definition. Those are the 2 points in the definition where we get to, sort of put stuff into rho, or start off with stuff in rho. And we always have to make sure that whenever rho maps any alpha to tau 1, tau 2, r, that r better belong to rel of tau 1, tau 2. And that's all we're doing over here. That it's an appropriate value relation that relates values of type tau 1 to values of type tau 2. Okay? And now just to finish this off, we pick a row that satisfies d delta, that satisfies our delta. We pick a gamma 1 and a gamma 2 that are related according to our environment gamma with rho. And if all of that is the case, then we say that our expression E1, we need to close it off, rho 1 gamma 1 E1 is related to rho 2 gamma 2 E2 in the expression relation for k steps at the type tau, carrying around the environment rho, which remembers our relation. Okay. All right, so that is the definition of the logical relation. Now, as I said before, you need to prove that every single one of your value relations satisfy the monotonicity property, right? So if, and this time you're doing it for an arbitrary tau. I won't write it. This time we're doing it for an arbitrary tau, which will include alphas, right? So we need to show that if that vk tau is a subset of vj tau whenever j is less than or equal to k, right? Monotonicity. And the alpha case will go through precisely because we have made sure that whenever we put a relation in rho, it is downward closed. Right? Rel says that. Okay? And then we basically prove the fundamental property of the logical relation. What is the fundamental property of this binary logical relation? Yes, okay. Fundamental property. Theorem. That whenever some expression is well typed, it must be related to itself. Okay? Does this look weird? Anyone have questions? Proving that will basically sort of, as I said about the fundamental property yesterday, the first thing you do after you set up your logical relation is you prove this property, which is where you end up establishing that the logical relation you've set up is, in a sense, internally consistent, if you will. Okay? Now, that's not all we need, right? Once we've proved the fundamental property, we need to prove, we started out saying, hey, we want a proof method that allows us to easily prove that two given expressions or programs are equivalent, are contextually equivalent. But proving contextual equivalence directly is too hard because it requires you to do this quantification over all possible contexts, and that's not tractable. So this is supposed to be our tractable proof method, but we have to show that it's sound with respect to contextual equivalence. So the next theorem that we want is soundness of the logical relation with respect to contextual equivalence or approximation. And that says that if E1 is logically related to E2 at the type tau, then E1 is contextually approximates E2 at the type tau. And similarly, of course, the statements for equivalence fall out immediately, right, once we have that. Now, before I say a few words about how we prove soundness, let me just put the statement of completeness up as well. So, completeness of the logical relation with respect to contextual equivalence. So this says that the opposite direction, that if E1 contextually approximates E2 at the type tau, then E1 logically approximates E2 at the type tau. Okay. Let me first say something about soundness, and then I'll come back to completeness, which is a really interesting sort of issue. Okay, so how do we prove the fundamental property? Yesterday I told you we prove it by induction on the structure of this derivation. All right? But the truth is, you don't want to prove it directly by induction on that derivation. At least not right away. You want to prove it you want to stage this proof into two steps. Okay? Step one of this is going to be proving a bunch of what we call compatibility lemmas. All right? So the compatibility lemmas are essentially a generalization of each of the cases that you would prove for the fundamental property. Let me explain what I mean by that. So the compatibility lemmas for the language that we have up here would be compatibility lemmas that we want to prove. So the first compatibility lemma that I want to prove would be X logically approximates itself. Well, that's a really easy one. That's exactly what you would prove if you were directly proving the fundamental property, so there's nothing different yet. Here's another one. Let's consider the lambda case. So I'm going to write it as an inference rule, but really I mean that the lemma that you want to prove is if the stuff above the line holds, then the stuff below the line holds. Okay. But the inference rule allows you to see that they're really just a generalization. They're coming from the structure of your typing rules. Okay, so I want to prove that gamma x colon tau1 dot E1 logically approximates, did I say gamma? Lambda. Lambda x colon tau1 dot E2 at the type tau1 arrow tau2 if I know that under the extended environment E1 logically approximates E2 at the type tau2. So given this fact, you want to prove this fact. So how is this different from if you were just doing the lambda case as part of the fundamental property? Well, it's slightly more general, right? It's allowing the two sides to vary. Over there, you'd be proving lambda xe is related to lambda xe if E is related to E. And the proof, the work that you're doing is going to be pretty much identical. It's just that you carry around different terms on the two sides, and this allows you to then it gives you a more general statement, which you can then use to prove the fundamental property, but more importantly, you need the further generalization when you get to the proof of soundness and completeness, because you need the two sides to be different there. Just take that in a nutshell, that's the reason. Yes?
I've been waiting to try to phrase why is it complexity? Why aren't there two terms of fundamental property?
Why aren't there two terms of fundamental property? Well, we want to know. So as I said, it's a form of consistency. But it's been a while. So okay. Let's look at what this is saying. This is saying if E is well typed, then it is related to itself. But this is a really powerful notion, this thing about related to itself. Let me explain why it's powerful. Because it says, if we look at the definition of this, that's down here, it says that you can run the same program twice, giving it related inputs, different inputs for the two sides. This is related to what Andrew was showing you with non-interference today too, right? Well, it's somewhat related. He hasn't quite phrased it that way yet, but maybe he'll get to it. So basically, this is also known as, by the way, we're doing system F. This is also known as parametricity, this fundamental property. Another name for it is parametricity in the presence of, in the setting of system F. Why is it parametricity? If people are familiar with the notion of parametricity or have heard anything about, about what it might mean, even vague statements, it will usually be stated as, yeah, parametricity is the property that you take related inputs to related outputs, which is kind of what I've been saying about logical relations, right? So it looks like it's not that general, in a sense, because you have the same thing on both sides, but it's capturing something about having one well-typed program that when you give it related inputs, it will always give you related outputs. And it is parametric with respect to whatever relations you pick in the middle there for your relating values of those two types, tau 1, tau 2, etc. Okay? That's sort of the best I can explain it right now. But in a sense, the compatibility properties that we're proving are more general, right? There are two different things on the two sides here. And that less general statement just follows from these. And I won't write more, but basically there's a whole set of compatibility lemmas, one for each shifting rule, essentially. Okay, so once you've proved those, you want to prove this. You prove this by induction on this, and now every case just immediately falls out from the corresponding compatibility lemma. So it's trivial once you've proved the compatibility lemma. And then you go and prove soundness. How much time do I have? I'm going to go for a bit. Okay, so you prove soundness. In order to prove soundness, you need one little bit of extra machinery. You essentially define this notion of a context being related to itself, or when are two contexts logically related. So we simply say that a context C1 is logically related, or logically approximates a context C2. Oh, I shouldn't be writing it that way. C1, C2 has type, the whole is delta gamma tau, type of the result is delta prime, gamma prime, tau prime. So this context, both of these contexts are well typed, they have the same type, same whole type and same result type. And these are logically related if for all E1, E2, such that E1 and E2 are logically related at the appropriate whole type. Then under delta prime, gamma prime, once you plug these contexts with E1 on one side and E2 on the other side, you get related expressions. So this is just sort of a device that lifts our notion of logical approximation up to the level of context. Then what we do is we essentially prove a fundamental property of sorts for context, which says that if any context is well typed, then it's related to itself. And using that, we sort of immediately get soundness. And all of this then keeps using the compatibility lemmas that we've already proved. All right? So if you want to see the details, look at that tech report that I mentioned. Okay? 2006 tech report. It has all of the details spelled out about how you structure these proofs. Okay, let's talk about completeness and why we would even want it. Okay, why would we want completeness? I think I said something about this yesterday. Why do you think you might want a theorem like completeness of the logical relation to hold?
Show
Show that two different terms are really different? No, wait, it's saying That if they're contextually equivalent, then they're in the relation? I didn't understand what you mean. I mean, it's trying to...
We have a kind of way to see whether a pair of terms belongs to states.
Yes.
And then we'll have a way to decide whether two terms are
right. Okay. Yes.
not really decided.
Not really decided, though, right? Because it's not a decidable proof separate proof method. Okay. So basically, in a nutshell, yes. When you have when you have soundness of the logical relation and you have the reverse direction, which is completeness, then that means that the logical relation is equivalent to the relation that we are calling contextual equivalence, right? So it seems like a good thing to have. It seems like if you have completeness in addition to soundness, then that means that every program that you could show using some sort of proof, every pair of programs that are in fact contextually equivalent, you should be able to use the logical relation to show that they are equivalent, right? That's not exactly what it comes out to in the literature. So if you go and read papers in the literature, you will often see a statement of soundness and completeness for the proof method. By the way, proof methods, there are two main proof methods for proving contextual equivalence. Logical relation is what we've been talking about. The other one is bicumulation. I don't know how much bicumulation is, but I shouldn't have. But in all these papers, you will see that the logical relation or the bisimulation is sound with respect to contextual equivalence, which is really critical. Otherwise, you can't really use that and say that that implies contextual equivalence. But the issue of completeness, like, you know, sometimes like you write a paper and some reviewer complains, but your logical relation isn't complete with respect to contextual equivalence. Now, we who work on logical relations and bisimulations know that this is a little bit of a red herring. You will go and often read papers which have this theorem proved, and then later on there will be a section, a discussion section of some sort in the paper which will say, yes, our logical relation or bisimulation is complete with respect to contextual equivalence, but here's a whole set of examples that you cannot really prove equivalent using our method. It's not strong enough to prove. Weird, huh? How'd that happen? Well, basically the issue is that it's all about how you build the logical relation. The way we have built this logical relation, I claim, is it's completely straightforward to turn the crank and prove things equivalent. We have not done anything weird to sort of make it complete. And by weird, I mean there are these technical tricks out there. The most prominent one that you will hear about is biorthogonality or top-top closure, which is essentially a way of taking a restricted form of contextual equivalence and building it into the definition of your logical relation at the appropriate spots so that your logical relation essentially becomes complete and this theorem goes through. Now, but what that means is that since in certain spots you have built in contextual equivalence into your proof method, now when you go to use that proof method, for the simple proofs that you could do before, they're still fine. But for the proofs for which this logical relation didn't really give you a nice proof method before, it will now still not give you a nice proof method because it's essentially saying, hey, now you're on your own, go fall out to the definition of contextual equivalence and use that to prove it. So, it's not the goodness of a logical relation or bisimulation. You know, how many examples and classes of things, classes of programs that can show it can be used to show equivalence is something that we sort of, in the literature there are papers which say, hey, we can handle this example. We can handle those examples that that guy couldn't handle. Oh, we can handle those examples that they couldn't handle. You know, it's just like a succession of papers building richer and richer proof methods, right? And especially when it comes to state, we are still sort of, in some sense, working on this. Okay. That's the thing to remember for completeness. And one other thing I'll mention, because you need to know it. You don't prove contextual equivalence implies logical relatedness directly. You go through another notion of equivalence called CIU equivalence. Okay, so if two things are contextually equivalent, you show that they are CIU equivalent, and then from there you show that they are logically related. CIU equivalence, all it does is, this definition talks about all contexts. This definition makes your life slightly easier by only talking about evaluation contexts, which are a subset of all general contexts. Okay? And then your life is a little bit easier and you can go there. And if you want to see the details of that spelled out, you can look at that tech report that I mentioned, or you can look at Andrew Pitts' chapter in ATAPL, because he also uses CIU equivalent, which is a notion due to Mason and Talcott back in 94 or 91. But anyways, the details of that are in Andy Pitts' chapter. All right, I'll stop there.